Good morning again, everyone. Welcome back to the last session before lunch. We're going to continue linking Python with other kinds of language with a talk by David Bowe. And David's a software engineer and former university tutor. In his spare time, David mentors the Drop Bears, a first FIRST, robotics competition team, and helps to maintain RobotPy, a project to bring Python to the FRC. And I'm a little bit worried about robotic drop bears, so we'll see if you've got them covered. Thanks very much, David. Give him a welcome.
I feel like this is a bit of an interesting duel to the previous talk, because I'm about to do basically the exact opposite, sort of. But let me set the scene a little bit. So perhaps you have a somewhat large C++ library that you want to ship to Python users, but you don't want to put in a lot of work into doing that. Or maybe you've written a C++ library perhaps for performance reasons, and you want an easy way to be able to use it from Python. So this is the sort of problem that we had with RobotPy, which is a project to bring Python to the first robotics competition. We have to deal with some reasonably large libraries, and both open and closed source. And this is because they do actually have to communicate with hardware. So we need to be able to call native code at some point. And to give you an idea of what the first robotics competition is, this is teams of high school students with adult mentors building 56-kilo robots to play a sporty kind of game. So you can see an example there. They get a new challenge each year to try to keep it interesting. So yeah, let's get into it. So one option that you might have is SWIG, or the Simplified Wrapper and Interface Generator. This lets you take some C or C++ and output a bunch of bindings for multiple different languages. And this is one of the oldest ones that I could find. And the fact that it works across so many different languages is probably a testament to how mature it is. And they do intentionally try to keep it as simple as possible. So this is a very simple example where you can take your header file for your library, and you can just include it. And you might want to ignore some things, maybe, because they're convenient for C, C++, but doesn't really make sense for Python. One of the other popular open source projects is Shiboken, which is one of the underlying libraries used by Qt for Python. Or if you've been around for a while, you've been using Qt, you might know it as PySide. That PySide project eventually became adopted by the Qt project and is now like the quote-unquote official bindings for Qt. And they use some XML to configure, which kind of looks like this, This is an example I pulled straight from their docs. It is a little bit intimidating though, so I'm going to break it down a little bit. And so here we have our first class that we're binding to. On the left-hand side is the XML. The right-hand side is the C++ definition declaration for it. Sorry. You can see we have two methods in there. But the XML only talks about one of them. So by default, all methods are exposed to Python. And here we say that we want some special handling for this clone method. Particularly, we modify what it calls argument index 0. That's the return value of that method. And here we're actually saying that the bindings should not destroy the object. It should instead let C++ deal with the memory management. Because we get a pointer, so it doesn't actually know necessarily how to handle that. And then we have this other class. There's a whole bunch of more methods, but what's interesting in the bindings here is that we also have a property that we can define. So you can just do truck.arrival message, and instead of having to call get arrival message and set arrival message to set it. And then we have a similar thing with memory management. And argument index 1 actually refers to the argument this time. So, yeah. And this takes us to the underlying library that we chose to use, which is PyBind 11. It's a C++ header-only library, so it's pretty easy to pull into a C++ project. And it lets you build a module, and you declare everything that you want to expose to Python in a C++ file. And it does let you also depend on classes from different PyBind 11 modules that have been built. I believe Shoboken does support this as well, but I haven't actually used it all that much. Let me know if that's wrong. But we'll see why this is important a little bit later. Here is an example of what PyBind 11 looks like. So on the left-hand side, I have my C++ code to have these bindings. First, we say that we're building a PyBind 11 module, and then next here is our module name. So to import this module from my Python code, I would say import PyCon AU example. And then M here is a variable name in the C++ code to say, this is the module that I'm putting together. So the first thing that we have here is we define an add thing. Specifically, we're putting the add function that you can see on the right-hand side, that declaration, and we're exposing that to Python. And then we have this pet class. So we say, I want a class called pet. We put that on the module, and it corresponds to the C++ pet class that you can see. So this first line here with the PyPack in it, that corresponds to the constructor here. And then we bind the setName, getName methods, fairly straightforward. And then we can also declare a property, just like you could in Shoboken. So this kind of takes us into a journey that we went through with a couple of our earlier approaches to generate all that C++ code that we would have to write otherwise. Because we have some fairly large libraries, right? So the first example that I'll show here involves a vendor library that provides a C interface. So we ended up building a library that can take a C++ header file. It parses it using a pure Python C++ parser. There were good reasons for this, but this library lets us generate literally whatever we want from a C++ header. So it takes in some Python code and a bit of YAML configuration that's provided to that Python code, and then puts it into a Ginger 2 template. So here's an example of what that sort of looks like. On the left, I have some YAML. So each top-level entry is each function that we want to bind to. You'll notice on the right-hand side, each of these take this handle pointer. So we decided to abstract that away and put it in a C++ class so that we don't have to deal with it. And then you can see here's something interesting. We can set some default values for some of these parameters, and you might notice that that's a default value in the middle here. That's because in our Python code we had set a global default for parameters called timeout_ms to 0. This is what the Ginger 2 template looks like to generate the C++ classes. It's scary. If you actually want to read the code, there's a link there. But this is then the template for the PyBind 11 code. I feel like you probably get the idea, so I won't show you the Python code that first preprocesses it. So, but yeah. So next example, we ended up getting a vendor library that only exposed an object-oriented C++ interface. So luckily, we already had all this generation code from that previous library that we built. So we decided to reuse some of it. So yeah, similar sort of setup with the same libraries, but different Python code, and the YAML looks a little bit different. So here we have this C++ class at the top, and then we declare a few different methods. You might notice, if you look at the right-hand side, there are two methods with the exact same name. This is called overloading in C++, where you can essentially end up calling a different function depending on what parameters you pass in. But in Python, this kind of ends up looking a little bit ugly. So what we did was we actually ignored this first method, and then we set a default for the second overload, because we dug into it and it turned out that the first overload actually just delegates to the second. I'll also note here, you might notice that these method names are Pascal case. So we turn them into camel case. This is because we already had a whole bunch of existing libraries in RobotPy that were all camel case. But this also lets students easily copy stuff from Java code, because there's a pretty healthy culture of sharing code within FRC. I don't think I need to show any more code for this. Hopefully you get the idea now. So that takes us to what we have today, which is this sort of generalized build system for generating these C++ bindings. So RobotPy build is a fairly opinionated build system for a Python package. So you declare it in your pyproject.toml. Reads your C++ headers, generates some pybind 11 code in the background, and it will also package up your shared libraries or DLLs in Windows parlance together with your Python package when you upload it to PyPI. We use C types to load it at runtime, so it works cross-platform, but a consequence of us packaging them together is that we explicitly don't support binding to system libraries. So if you need to use libraries that you have installed in your system, you might be better to use Swig or Shaboken, or write pybind 11 code yourself, I guess. Sorry. But yeah, so we end up with these data files that describe what headers to look at in this library that you're building for, what names you expect, so both functions, classes, enums, things like that, and also any particular special handling that you might need. So to give you an overview of what our dependency graph looks like, this is just the dependency graph for the same library as our previous example just now. You might notice there's a whole bunch of different, we've got diamond dependencies, and there's also subclassing of classes from each of these different libraries as well. So this is where the pybind 11 support for cross-module class usage comes in, because we've got this vendor library that has to be able to subclass an interface that one of our other libraries provides. So this is what the pyproject.toml looks like. So at the top, we say that we want to download our vendor library, in FRC we've set up this standard convention that's Maven based for where to find libraries, and then we start talking about our actual pybind 11 wrapper. And you can see there we have this depends list. This lists other packages that we've built using RobotPy build, and this lets us actually link to those other packages. And then at the bottom, we have a list of headers that we want to look at. This is just an excerpt, so we're just going to be focusing on this example here. this is the same class from the previous example as well. So there is a little bit of new things in here where we have this keep alive thing. So what this does is it's part of Python 11, and it lets you bind the lifetime of one object to another. So in this case, so here we have 0, which is our return value, and 1, which is self. So this is saying that this PID controller thing that's returned by this method, make sure that it doesn't outlive this can spark max. So whilst you still have this PID controller object, the can spark max object would not be garbage collected. And then at the bottom here, we have a bit of inline code. So this lets you shove some C++ code into the Python 11 module that's eventually generated. And this allows us for infinite customization. So here, we actually add a method to the Python class that doesn't exist on the C++ class. Specifically here, we're adding a dunder repr method just so that our users, which are high school students, can more easily debug their robot code, right? They don't care about the memory address, which is what the default repr is. There are other PyBind 11 auto-generators out there. Some of them are listed from the Python 11 documentation, which I have also listed here. I haven't had an opportunity to try them out, but they do actually use Clang, an actual C++ compiler, rather than a C++ parser that's been written in Python, which does solve a lot of the edge cases in having to parse C++ because it's a lot harder to parse C++ than you might think. Okay. So you might be wondering then, how do we ship all these libraries to our users, right? We basically just want them to be able to pip install RobotPy and things work. So what we do is we build a bunch of wheels in CI. We have a lot of repos, so we created this reusable workflow, which is a GitHub Actions feature where you can say, hey, this CI pipeline should just run this CI pipeline that's defined in this other repo. Now we build for the 3 big operating systems for all the currently supported CPython versions. So that ends up being 15 wheels that we upload to PyPI. And we deploy these whenever we push a git tag. So that's part of the CI pipeline as well, is that it checks whether we've just pushed the git tag. And we also build a bunch of ARM wheels as well, and we have a private repo for those. This is because the main controller that's used in FRC is a bit of an unusual Linux ARM platform. But we do also target Raspbian, but because ARM is so diverse, right? Like what, as Jimo said, like what ARM are you talking about, right? So we decide that we don't want to deal with that when uploading to PyPI, and users have to explicitly opt in to actually using our ARM wheels. Now, our wheels do technically fail audit wheel, which is the many Linux auditor. And this is because of our cross-package library dependencies. They do otherwise satisfy many Linux, as last time I checked. So we just end up renaming the wheels in CI just before we upload to PyPI. And we haven't had complaints, so I'm pretty sure it works. That's all I have. If you want to check this out, there's a link to our repo and our docs. We also have a Matrix channel, and yeah.
Thank you very much, David. We've got a little bit of time for questions. I'm curious about how many other, is it used on other robot platforms or on other C++ projects yet?
So I do believe that one of our co-maintainers, the main maintainer actually, has used it at work. I'm not entirely sure on the details because work stuff, I guess. But yeah.
Yeah, cool. There's a question at the front.
Question I had was why you went down the route of auto-generating the PyBind code rather than handwriting it.
That's a good question, yeah. So the libraries that we had to package are actually very large. Like in one of our libraries, we have I want to say at least 50 different classes. There's also one of our packages is a very maths heavy, and so there's a bunch of classes in there, and we want to use C++ for performance reasons there. But then, actually, yeah, that's all I have.
Cool. Any other questions? Or just one at the back? Yep.
So I was just curious if you'd looked at using CI build wheel to solve some of those audit wheel compatibility issues.
It's a good question. I did have a brief look at it, but I'm not sure that CI build wheel supports the Ubuntu versions that we have to actually target. This is a good question. I'll have to double check on that.
Cool. Anyone else? Oh, just one. Yep, time for one more.
Hello. Just wondering if your approach works with very heavily templated libraries or header-only libraries.
Yes, excellent question. Yes. So a few of our libraries are actually pretty template heavy, and so we do have explicit support for that in RobotPy build as well. You do have to manually list out all the template instantiations that you want, but yes.
Very cool. Please join me in thanking David once again. Here's the mug. Thank you so much for that.